A hidden force is lifting the Appalachian Mountains right now. Nearly 500 million years ago, the world looked nothing like it does today. The land that would become North America lay scattered near the equator, surrounded by warm, shallow seas. The air held no scent of grass or forest. On land, there were no trees, no ferns, not even moss. Life clung almost entirely to the oceans. In this alien landscape, the first act in the story of the Appalachian Mountains began. Geologists trace the origins of this ancient range to around 480 million years ago, deep in the Ordovician period, when continents collided in slow motion over millions of years. These collisions would happen 4 times, each one reshaping the face of the continent and building mountains that once rivaled the heights of the Himalayas. Yet the Appalachians predate even the earliest land plants. Their rocks remember a time before roots held soil together, when bare stone faced the elements alone. The sheer age of these mountains, older than trees, older than land animals, sets the stage for a geological mystery that still puzzles scientists today. The Appalachian Mountains rose through a series of immense collisions that spanned more than 1 billion years. The first of these, the Grenville event, occurred over 1 billion years ago, forging the deep crystalline basement that still anchors the region. Hundreds of millions of years later, the tectonic orogeny struck between 470 and 440 million years ago, when a volcanic island arc crashed into what would become North America. This collision piled up mountains and thrust ancient seafloor rock skyward, forming the earliest recognizable Appalachians. Next came the Akkadian orogeny, about 375 to 340 million years ago. Here, a microcontinent called Avalonia slammed into the continent's edge, folding and fracturing the land and adding new layers of height and complexity. The final act, the Alleghenian orogeny, unfolded between 325 and 260 million years ago, as the landmass that would become Africa collided with North America. This last collision completed the supercontinent Pangaea and pushed the Appalachian peaks to heights that rivaled today's Himalayas. Each collision left its own mark, distinct belts of deformed rock, metamorphosed layers, and buried faults. These orogenies built a mountain chain that once towered over the landscape, constructed in phases by relentless tectonic force. Yet, after the Alleghenian orogeny ended, the forces that built the mountains gave way to the slow work of erosion, setting up a stark expectation. Over time, even the mightiest peaks should wear down to low, gentle hills. Geologists have long expected that after the last great collision ended 180 million years ago, the Appalachian Mountains would spend the rest of their days being worn down by wind, rain, and rivers. Erosion, relentless and patient, acts as a natural leveler. Over tens of millions of years, even the tallest peaks surrender to gravity and weather, their sediments swept away and deposited far from their source. The evidence for this process is written in the rocks offshore. Vast sedimentary wedges, hundreds of kilometers long, built from debris stripped off the ancient highlands. By the late Jurassic, around 150 million years ago, the Appalachians had been reduced to a low-relief surface called a peneplain, a landscape so subdued that it barely rose above sea level. Geomorphic models and sediment budgets suggest that more than 1 kilometer of rock vanished from the range before the Atlantic Ocean began to open. The expectation, grounded in these numbers, is straightforward. An ancient mountain belt, left undisturbed by new tectonic forces, should eventually become a landscape of gentle hills and broad valleys. Yet, the present-day Appalachians confound this prediction, setting up a puzzle that remains unsolved. Mount Mitchell rises above the Carolina forest, its summit reaching 2,037 meters, higher than any other peak east of the Mississippi. The view from the top stretches across sharp ridge lines, deep gorges, and valleys cut by tumbling streams. For hikers, the climb is a reminder that the Appalachians are anything but gentle hills. The steepness is not an illusion. The Blue Ridge and Smokies still carve an unmistakable profile against the sky. This rugged landscape stands in stark contrast to what geology textbooks predict for a mountain range of such age. The Appalachians predate the first trees, their rocks shaped by 4 massive continental collisions, with the last, known as the Alleghanian orogeny, ending nearly 180 million years ago. After that, the mountains entered a long era of erosion. By the late Jurassic, more than a kilometer of rock had been stripped away, leaving behind a landscape so flat it barely rose above sea level. Yet the evidence on the ground refuses to fit the script. Mount Mitchell towers over the landscape, and the Colassaga River Basin has seen its relief grow by more than 150% since the Miocene. 14 distinct nick points, sharp drops in river elevation, cluster between 1,250 and 1,530 meters, tracing a pattern of recent downcutting. Beryllium-10 dating reveals that some of the bedrock exposed in these gorges has seen daylight for only about 6 million years. The contradiction is plain. An ancient range, expected to be worn flat, still shows the marks of a young, rising landscape. Geologists like Dr. John Gallen, who have mapped these features, point to a puzzle that challenges the fundamentals of mountain evolution. The question hangs over every summit and gorge: what force is keeping the Appalachians high? Digital elevation models have revealed a pattern that defies the logic of steady erosion. Over the past 12 million years, the Colassaga River Basin has experienced a surge in relief, more than a 150% increase, far beyond what climate or river incision alone should produce in such ancient terrain. This change isn't limited to a single valley. A corridor of uplift stretches nearly 350 kilometers across the southern Appalachians, cutting a swath through landscapes that should, by all conventional models, be worn low and flat. Dr. Robert J. Parker, a geomorphologist whose fieldwork has mapped the region in unprecedented detail, points to this corridor as the clearest numerical evidence of recent vertical motion. Using high-resolution DEM data, Parker and his team traced the transformation of the Colassaga and neighboring basins. Their analysis shows that the current topography is not a relic of ancient mountain building, but the result of renewed forces lifting the land in geologically recent times. The data leave little room for ambiguity. Relief in the basin has more than doubled since the Miocene, with the uplift corridor aligning precisely with areas of steepened slopes and deepened gorges. These findings set the stage for a closer examination of the region's river profiles, especially the sharp clustered nick points that serve as markers of this ongoing tectonic mystery. Dr. Robert Parker's fieldwork in the Colassaga River Basin uncovered a striking pattern. 14 sharp drops, known as nick points, etched into the river's course. Each nick point marks a sudden change in elevation, with most clustered tightly between 1,250 and 1,530 meters above sea level. The vertical drops at these points range from 100 to nearly 200 meters, slicing through otherwise steady river gradients. These features are not scattered at random. Instead, they align within a narrow band, hinting at a shared cause that has reshaped the landscape in recent geological time. Parker's team mapped each nick point with high-precision GPS and cross-checked their measurements against digital elevation models. The survey revealed that these nick points are not controlled by changes in rock type or by fault lines, a detail that rules out many familiar explanations. Instead, the uniformity and clustering suggest a regional force at work, one powerful enough to push the land upward and force rivers to carve new paths downward in response. The presence of 14 distinct nick points, all perched within a 280-meter elevation window, stands as physical evidence of recent uplift. These are not relics of ancient mountain building, but fingerprints of ongoing change. The rivers, in cutting through these nick points, record the pace and pattern of the land's vertical motion. This inventory of geomorphic markers sets the stage for a deeper investigation. Exactly when did these surfaces last see daylight, and what force is driving the transformation? Beneath the dense forests and rolling summits of the southern Appalachians, a hidden clock is ticking. To measure the true age of this landscape, not the rocks themselves, but the moment when the surface was last stripped bare, scientists turned to cosmogenic beryllium-10. This rare isotope forms in quartz when cosmic rays strike exposed rock, accumulating in tiny amounts over time. Dr. Emily G. Rosen, a geomorphologist with the USGS, led a series of field campaigns into the Kulasaja River Basin, collecting samples from freshly exposed bedrock at the base of steep gorges and along the sharp nick points that stagger the river's course. Laboratory analysis revealed a surprising pattern. Most of these surfaces have been exposed for only about 6 million years. These beryllium-10 ages cluster tightly around the Miocene, suggesting that the land here was rejuvenated far more recently than the mountain-building events that shaped the region. On rock that predates the first trees, the surface itself is, in geological terms, young, evidence that something has lifted and exposed these ancient stones within the last few million years. 4 main theories stand in uneasy competition to explain the Appalachian riddle. Dr. Andrew Humphreys points to a mantle anomaly, a region 350 kilometers wide and up to 200 kilometers deep, where seismic imaging reveals the mantle is 150 to 200 degrees Celsius hotter than its surroundings. This heat makes the crust more buoyant, potentially lifting the mountains from below. Dr. Jason Weaver's research suggests a different mechanism: flexure of the crust in response to ancient subducted plates, where buried slabs cause the lithosphere to arch upward long after collision. Dr. Chen, speaking through published interviews, raises the possibility of isostatic rebound. As erosion strips away rock, the crust loses weight and rises, though models indicate this alone may only account for a fraction of the observed uplift. A fourth school of thought, represented by climate and geomorphology specialists, argues that changes in rainfall, river incision, and differences in rock strength can mimic uplift, producing sharp relief through differential erosion even without deep tectonic forces. No single theory fits all the data, and each carries unresolved questions. The debate remains open, with the mountains themselves as the silent witnesses to processes that may still be unfolding. Ancient mountains, 480 million years old, should lie in quiet ruins. Yet Mount Mitchell still rises 6,684 feet, and the Kulasaja Basin's relief has surged 150% in 12 million years. Competing theories persist, but no consensus. The Appalachians remain an open question, proof that even settled landscapes defy final answers.